Okay, so let's continue. Um, so last time we talked about alternating like least square methods. That's a very popular one. Another one that being and used a lot, it's called matrix normalization. Uh, sorry, minimization. Um, so so we can rephrase this problem. I mean, to following that. So basically, and I want to remind you. And previously, we need to specify the dimension of the latent feature space K. So that means we need to specify the rank of the matrix. Um, but um, but the question is, how do we find out this and rank a matrix, right? So what we can do is we can rephrase things in a different ways. So we can and rephrase as follows. So this is I mean the following optimization problem is I want to minimize actually some called a theta, the rank of the theta, such that subjected to this theta ui is equal to AUI. So basically, I want to find out a low rank matrix theta such that all these observations actually matched, and they are in the low rank. All right. So I mean, with that, the benefit is we don't need to specify the K. Which is good things, but there are multiple issues, right? The first issue is this is NP-hard problem. So basically, and I mean, if you don't know what is NP-hard problem, so that means that this is extremely difficult problem and to be solved. There is no good efficient algorithm can be solved. So basically, it would take almost forever to solve these problems. And also, here, I want this to have exact matchings that my theta ui equal to AUI. But in practice, you won't get exact matchings. Maybe one or two entries is being off. But being off of one or two entries is perfectly fine. It's considered as a like an error. Okay, so what? And obviously, that's not so a very good ways of solving everything. So you can think about my previous approach is kind of like relaxation of these problems. It's like relaxations of this, non-convex difficult problems. Of this hard problems. So this is actually very, very hard. So basically we cannot solve. Okay, so can we find another way to relax this problem and hopefully can make things a little bit easier, or maybe come up with a different penalty, all these kind of things to help it out. So let's and let's like set back and to see what is the I mean, might have other and a good method and to solve these problems. Okay, so let's think about and sit back to think about different problems first. So I promise we will come back to this later. Say if you are given a positive semi-definite matrix, positive semi-definite matrix. Let's call it M. This M is in the space of D by D. Okay, so by definition, since it is positive semi-definite matrix, the lambda I has to be bigger or equal than 0 for I of all these eigenvalues. Okay. So what is the rank of the M? First thing is the rank of M is actually the number of positive and so the number of positive values. So number of positive eigenvalues. So that means I'm counting the cardinality of my lambda I such that my lambda I is strictly positive. Okay, so that basically it's you can think about a zeroth norm of lambda if we treat lambda as being a vector here. So these two things are equivalent, and the rank of that positive semi-definite matrix and the zeroth rank of its corresponding eigenvalues. So what we can do, but this is basically impossible to calculate in general because this is very hard to calculate. So that's why to minimize the rank, that's nearly impossible. So the trick is we are using one norm to approximate the zeroth norm. So what does that mean? Is this is actually is approximated by the one norm of the lambda as a vector, which in this cases, it's easier to be calculated, which is just the absolute values, sum of the absolute values. Okay, so, and which is basically the one norm, which is basically the trace of the matrix. Okay, so this is like much easier to be handled. So that means we can find a way to relax these problems, right? So we're trying to minimize this rank, but we know this rank is basically equivalent with the zeroth norm of that matrix. Okay. So what we can do is we can relax this problem in a different ways. So relax it. Okay, so but if you want to relax it, here we have one assumption here. Assume A here is positive semi-definite matrix. Okay, but I mean this is not always true. But say this is just positive semi-definite matrices. All right, this can be relaxed by replacing the rank by the trace. So this becomes, instead of you minimize the rank, you minimize the trace. This turns out to be much easier to be solved. So this is basically the one norm subjected to the theta ui equal to AUI. Okay. And also we need to assume this A is positive semi-definite matrix, and also my theta is also right here is semi-definite matrix, bigger or equal than 0. So I mean, this notation means this matrix is positive semi-definite matrix for U and I in omega. Okay. But of course, like, I mean, this is not ideal because we have this assumption right here. So this A has to be positive semi-definite matrix. But what if I'm interested in the rectangular matrix, right? And I feel this rectangular matrix, and can I have similar analog to it? What if A is rectangular matrix, which is the cases that we are interested in? Right, so this is in n by n, say, right? So it's rectangular. All right, so we can do similar things like that, but instead of we using one norm or the trace, because it's trace, you cannot define the trace for the rectangular matrices. So what you can do is, so this is the key here. The key is use something called nuclear norm. Of theta. So what is a nuclear norm? Is here we have, I mean, basically this is the sum of the absolute values of the eigenvalues. But I want to remind you, if it is positive semi-definite, then the eigenvalues and the singular values, they are the same. Right? So basically eigenvalue decomposition is the same as singular value decompositions. But in rectangular matrix, we don't have eigenvalue decompositions, but we always have singular value decompositions. Okay. All right, so we can change this one norm into the nuclear norm. This becomes following. So it becomes the nuclear norm, which is the star right here. By define, the nuclear norm is the sum of the singular values of the theta. So this is a very important, and also we have the same constraint subject to theta ui equal to AUI. All right. But here, I mean, since we don't assume this is to be positive semi-definite matrix, so theta can be a rectangular matrix. So in this cases, we solved this problem that basically we relax this NP-hard problems To furthermore, in this case, it turns out to be a convex problems. So this is related to convex problems. So, I mean, probably have learned this in optimization that if it is convex, it is usually relatively easier to be solved. Okay. But the issue is this, I mean, it's not strictly convex. So that means there's still, has a possibility it don't have the solutions. So that means in order to have a feasible solutions, we need to solve the second problems. Sometimes we won't get exact matchings, right? So we need to consider the situation that this, don't have the exact matchings. So we need to further relax and relax this like constraint conditions, right? And this constraint is pretty strict. So and sometimes we want to study something that is not that and a strict constraints. So we need to further relax. And actually further relax to the following that I'm going to adding this as a penalty, basically. So we have same thing, it's nuclear norm. So we have so we're adding this and constraint to be a like and the mean square error. Plus being the nuclear norm being like an additional penalty terms that we're trying to minimize. So this is basically kind of think of a choice of the norm. So I want to remind you, if it is in the ridge regression, this is L2 norm. In Lasso, this L1 norm. In this and the recommender system, which is explicit and feedback situations, it's likely you are going to have the like nuclear norm being your penalties. This time, this is not only a convex, this becomes a strictly convex. So that means actually it's a unique and it can have a unique solutions. Okay, so this is very good. So basically, so with that, it's usually being solved by like and solved by so algorithm called SDP. SDP is short for semi-definite programming. Okay. All right. So that's basically that, and then I'm going to give you a short comparison here. So here is the short comparison that we have. So this is, we're trying to solve this low rank solutions. We have talked about this. So you think about it, we are trying to solve A equal to W inner product with H transpose. And this is basically, you can think about the mean square error. And we are adding a penalty of the and Frobenius norm of W and H. So the advantage of the last lecture's approaches is I have like number of parameters that we work at is smaller because and we only work with n by k and n by k matrices that we can get. And we can have a very fast solvers. Well, and okay, that solver is ALS. However, the problem is we might have multiple local optimal. So this problem to solve this low rank solutions is in generally non-convex. If it is non-convex, that means it highly depends on the initial conditions of your W and H. If your initial condition of WH is close enough, then you can find the solutions that you need. But if it is farther, away, it might be trapped in some other local minimums. On the other hand, this is the thing that we use the nuclear norm minimization. So this is, this part is still, you think about this as being a matrix and the mean square error of the matrix. But in this time, we are actually trying to find out the theta, itself directly. Theta here is n by n matrices, right? So, and we have m times n entries need to be found out. Here, I want to compare with the WH. This is m times k and n times k, which turns out to have a significantly smaller number of the parameters. But for this nuclear norm and minimization, it has several good advantages, which this directed solver of the low rank solution don't have. One is, this problem is a strictly convex, not only the convex, but like strictly convex, and also has a global optimal solutions, and that solution will be very close to truth, right? So that's exactly something that you are looking for. But the problem is, the advantage is, this is usually being solved by, as I said, something called SDP, semi-definite programming. This can be very slow if this theta is really large. For example, if you are working with that Netflix price, that matrix is very big. It's too big, even you cannot save this matrix in your own computer. In that cases, this SDP will be very, very slow, although this is still in polynomial time. But in general, people don't use that kind of the algorithm on such large matrices. So this is basically simple comparisons with these two methods. And of course, in 2004, people has found out, in fact, this direct low rank solution that we're having is a non-convex approximations of nuclear norm minimization. So basically, you can think about this something here is kind of the kind of like approximation of this nuclear norm minimization problems. So it turns out if we pick the rank k right here is slightly larger than the rank of theta that we're interested in, the local optimal of our solution is actually always the global optimal in the nuclear norm minimizations with high probability. So basically, the key here is, in fact, yes, this problem is still, it's non-convex in general, has a lot of local optimal. But if you choose the k in the right way, which is slightly larger than the rank of theta, you just happen to be that much of the choice of k, it turns out this problem is actually convex. It actually only has one unique solution, which is the global optimal that we are looking for. And your algorithm can you can just apply an ALS algorithm for us and for that problem. And we can show it actually can always converge to this global optimal that we are interested in with very high probability. So this is a very and a significant result. So basically, if you make the choices k correctly, you can always find a good solutions. All right, so All right, so that's one thing. Okay, next, let me share with to my iPad again. All right, so this is the second approach, and also mention about the connections between these two approaches. The next one is method 3 is non-negative matrix factorizations. Okay, so right now, I want to remind you my W and H, right? So we have, I want to remind you my A is I want it to be approximately equal to W as a matrix of times H transpose. Okay, so W is basically in terms how much the user like for each topic. Okay, so this H actually can be interpreted how much this movie contribute to the topic. So naturally, you have, this implication is each entry of my W and H has to be non-active. So this has, and these two things has one big implication, that is each entry of W and H are non-active. Right? Because so I want to say how much the user like those topics. It is negative. What does that mean? Does that have meanings? And so the meaning is, is problematic. So that's why we need to, and hopefully find out this. Solutions for W and H actually give you non-active solutions. But my method 1 and method 2, which is the low rank and the directives, so low rank solutions, and the nuclear norm minimizations can still produce a negative result. Can still produce the negative entries. Okay. So that means if you want each entry to be non-negative, so that means I need to put this as like constraint. Okay, so here is my, and here is my, and the constraint optimization. Okay, so basically, what you need is you have minimization of W. Okay, and so my W is M times K, and my H is in N times K. I have a 1/2 summation UI in omega AUI subtract the WU. It's the same thing, right? So that part is the same. HI transpose square plus the penalty this is exactly the same. So what is the differences here? Is I'm going to add the constraint. So the constraint is subjected to, this is W is bigger equal than 0 and H is bigger than equal than 0. So you can see right here, W right here is actually a rectangular matrix and H is a rectangular matrix. If I using this notation on a rectangular matrix, that means this is actually, I'm saying this is, and each entry has to be non-negative. Okay, so there's multiple methods. Okay, so, and it can be done. One of the method which is being quite popular is basically called and projected gradient and algorithm 1. Again, and so you probably learned that in optimization courses. But if you think about what is the idea of the and a projected gradient, say you have some constrained space. So you want your solution to be in this constraint. Say this is your and a parameter at the point that is, say, theta of t, right? So then you're trying to solve this with certain kind of iterations, gradient descent or whatever things. But on the next step, say it just, if you, using gradient descent without even like, and so worry about this constraint, it will shoot up outside of this domain. So this is actually, say, your next step of theta. However, right here, this is outside of this domain. So that means what I'm going to do is I'm going to project back. Okay, so this is actually, we project back theta 2 into theta t plus 1. Okay, so this is basically a way to say and projecting the theta to the t plus 1 onto the constraint domain theta t, and that becomes the satisfied and the theta t plus 1 since it satisfies the constraint. Okay, so basically, and to be described in more like way that we can think about as follows. And as I'm going to using the framework in the stochastic gradient descent. Okay, so this is much more popular one that we are doing here. So I want to remind you, previously, I'm going to compare the differences. So you keep iterating. So first thing that you do is you randomly pick a pair, I and J. So let's call it U and I, okay? Think U and I. Omega. So, and I want to remind you previously, right? So, we have WU, it's 1 minus eta T lambda minus eta T WU H I transpose minus AUI HI. Okay. So this is, I mean, the method that we have been using before. But here I'm going to make some modification because this U W and the WU here maybe go out and go outside of this constraint, right? So like what we are getting here. So I was previous here at one step in my goes to outside of this constraint. So basically here is the changes is I'm going to put a tut here. All right, so the new step is the real WU is actually I'm going to project back onto the constraint. So basically it's WU tut plus. So what is this doing is set all negative value to 0. So basically, if it is negative, it will be projected to 0. Same thing, if you remind you, the H of I is being, I think I missed something here. I missed the WU here. Right, so this is 1 minus eta t of lambda of H of I subtract eta t WU HI transpose minus AUI WU. So this is basically the second step, and here obviously this is my go outside of the constraint. So this is actually has to be replaced, right? So and project back into 0. Again, set all the negative values to 0. So this is projected and a gradient descent. All right, so this is one method. Another another way that we can do is a very popular method called Lee and Sense multiplicative update rules. Sense rule. So, I mean, this is a very popular algorithm. So what actually happened is the following. And in fact, this is being and used and get like, and it becomes like very popular here. So but let me just try a different color, maybe this, okay. So so that, I mean, in DLSN, that optimization problem is slightly different. So it doesn't have that half here. So it will be as following. So this is being and replaced in the following equivalent matrix form here, and we have the has the like entry-wise form, but actually what we are trying to do is we are trying to compare the Frobenius law, right? So here is actually the equivalent form in the matrix form. In the matrix form, is the following. So it's the minimum of my W and H, where W is m times k. H is n times k. All right, so I mean, in terms of the matrix form, this is A minus WH transpose. And the lambda, so I think I have 1/2 here. And the lambda over 2, which is the same thing. Right, so I mean, this is penalty subjected to W is bigger than 0 and non-negative, and H is non-negative as well. All right. So there are some like linear algebra stuff that is relevant. It might be helpful to and for us to and to solve this problem. So this some like and a background information. First, if this is a matrix, if you are interested in the square of the Frobenius norm, it's equivalent with the trace of X transpose of X. The second is gradient of X of trace of A times X and A transpose. Gradient of X, trace of XA transpose of A. Trace of X times A and XA transpose. This is equal to X times A plus A transpose. So these are some like identities in terms of matrix calculus. It turns out these will be extremely helpful. So we can try to expand things a little bit. So the first things will be helpful is this term. Right, so here, this A minus WH transpose. So this term, in fact, you can using the first property that can be written as the trace of A minus WH transpose of A minus WH transpose. Okay, so you can actually expand this. If you actually expand this, you are getting something like trace of A transpose A minus trace of A transpose of WH transpose minus of trace of HW transpose of A plus trace of HW transpose WH transpose. Okay, so these are the four components. So this whole thing is actually non-convex with respect to W and H, but turns out it's actually convex in only W or in only H. So that means we can using similar like ALS, alternating least squares, or sometimes we call it block-wise coordinate in the descent schemes to optimize with respect to W while keeping the H fixed and vice versa. So this is basically very, very similar to ALS. but we're trying to process everything in terms of in the matrix form. So basically, I mean, this has nothing to do with the W and H is treated as constant. For example, the first term of the trace of A transpose WH transpose is equal to, I'm going to using the fact that trace is cyclic, then you can rotate things as well. So basically it's trace of ABC is equal to trace of CAB. So this is becomes a gradient of trace of H transpose, A transpose, and a W. Okay. So then this we can using the second property right here. So this actually give me H transpose, A transpose, and the transpose. So this is equal to A times H. All right. So we can do similar things for the rest of, and the second one. I'm not going to do it. Just like write down the solutions. H like this. So you can like basically rotate things again. This is the trace of W transpose AH. This is equal to AH, which is the same. The third terms, the trace of HW transpose WH transpose. So this is the quadratic term. Again, we do this rotations of the trace of WH transpose HW transpose to WH transpose H. Okay, so this is that. So basically, if we combine this together, and also we are missing this part, which is the gradient of Frobenius norm of 1/2. This is actually equal to, I believe is just equal to W, right? So this is basically how you do the derivative with respect to a matrix. Okay, so and you can combine these things together. Then we have a half, like and basically 1/2 just cancels out with a 2 here. The gradient of W, let's call this whole thing as, I think I have a name before. So this is, I call it defined as F of W and H. Right, so basically if this is F, W, and H, this is equal to the WH transpose minus A times H plus lambda W. And you can do very, very similar things for take derivative with respect to H. So this is very, very similar to alternating least square, but the difference is in alternating least square, what we do is we are doing this with the index form. This is actually, we are doing this with the matrix form. All right, so this is the difference. So this is like that, subtract of A plus lambda times H. All right. So with the derivatives that we have, that we can update our W and H accordingly, right? So this is derivative we can using gradient descent methods to update my W and H. So again, my W here is being updated. So this is gradient descent methods. The W is updated as following. So this is basically a very simple way of approaching everything. Same thing for the H. Eta H lambda of H, subtract eta H, W transpose, WH transpose minus A. So, but you said we haven't addressed the non-negative part, right? So this right here can still be negative. I mean, so those entries can be negative. Why? Because here my learning rate here, right here, these learning rate step size are positive. So that means we are subtracting something that is positive. That's why it can lead to negative elements. So, I mean, in fact, this is kind of interesting, but like, for example, can we manipulate? And the Lee and Sense idea is we acknowledge of everything, but what we do is, can we just design an eta of W and eta of H such that this, I mean, we can avoid subtract a positive problems. That's why, I mean, subtract a positive value may give you some negative element, which is not good. So that means if we can avoid subtract the positive value, so if we start a positive, it's always give you positive. They always give you positive. Right, so this is a very simple idea. Can we design an eta W and eta H, which is the learning rate, such that we can avoid these subtractions? It turns out we can. So this is something interesting, but it's not that straightforward though. So here is the methods. Here is the key. So the key insight is I'm going to say when we update the wij. Okay, so this is the key here. So, and this learning rate, eta, is different for each entries. So it's entry-wise different. If I set the learning rate as wij, so and lambda wij plus wh transpose h of ij. So that means, and this is like entry-wise or element-wise adaptive. Okay, learning rate. So this is one of that. Another one for h, ij. So this will be h, ij divided by lambda hij plus w transpose w h transpose ij. Okay. So if we allow this one, we can adding back, see whether we and what kind of things that we're getting. So let's see this one. So this w subtract this lambda, and let me just combine the bottom here. So this is, and so let me just rewrite things a little bit. Okay, so this is, I'm getting the w and subtract eta w times lambda of w. Subtract eta w, wh transpose h plus eta w a h. Right, so, and you already see something interesting here, right? All right, so all right, so you see this part and this part, they are always positive. Just these two might create a problem of the negativities. So I'm going to combine those positive part because my w, if you start positive, it always stays positive. So w plus eta w of ah subtract the eta w of lambda w plus wh transpose of h. Okay, so this is basically here. Okay, so here I'm going to do things is I only consider the entry of ij, entry of ij, same thing. So this is basically wij plus eta wij of ah ij, then minus the eta wij of the lambda wij plus h this ij. Okay, so this is basically only consider the ij entries here. So if we do this, we will find out this actually this multiply the denominator right here, it get me wij. This is equal to because this multiply this, if we just happen to choose this adaptive learning rate, this becomes Wij. And this becomes eta Wij times A times Hij. With that, it is strictly positive because I don't do any subtraction now. These two just cancels out. What actually left is always positive. Positive value multiply positive value is positive values. Okay, so this is and this is very good, and we can actually write it up. So this is Wij times Hij, and it divided by lambda Wij plus W transpose Hij. So obviously this whole thing is positive. So this will be your algorithm. Actually, you're going to replace this Wij by this. So this is the update rule for W. Okay, you can do the same thing for the H as well. So you have the update rule for Hij. This will be, you do the same thing. This is Hij, W transpose of A, Ij divided by lambda Hij plus W transpose WH transpose Ij. So this is again strictly bigger equal than 0. This is update rule for Hij. So this is basically if your initial condition H is non-negative, it will stay non-negative because I don't have any subtraction right here. If we just happen to choose this very specific adaptive learning rate. All right. So and also this update are done on the element wise basis. So basically each Ij you can do it separately. So it's not actually matrix multiplication. So you can do the matrix multiplication right here. But once you are done, these matrix multiplications, everything else is being performed element wise. Okay. So this is good. So this is really good. So I don't want to. So yeah, let me show you this. The final algorithm right here. So basically, if you are given a partially, if you are given this partially observed A right here, and you have some initial value of this non-active W and H, it has to be non-active. So what you do is you just iterate through this update rule that I just write here, right? So, and you have your current HT and the current WT. You do everything entry-wise, right, for this IJs. So you loop through all these IJs. And also right here, since you already updated W, and you can just using the updated WT plus 1, right? So you keep doing this update. So this will be your update rules for Lee and Sense update methods. So this can ensure this is to stay non-active. But the issue is this algorithm cannot take advantage of stochastic gradient descent. So in this case, it's because and everything is sequential, you actually need the result of periods to get the future values. So you cannot just do everything in parallel. as well, and there's no stochasticities. It's always deterministic. So in general, it will be slower, but you are sure this will be on the non-negative side. Okay, so at last, I don't think I may not have time to talk about the code. I may have time, but I can postpone that to the third lectures, right? So that might be a little bit easier for that. But I want to talk about this feature-based recommendations, which is the fourth method. This is also a very, very popular one. So here we assume, and the only information that we have is integer ID of the user and integer ID of the movies. This is very bad representations because and think about, you have all the data you already have, the matrix you already have. But if you wanted to have a new item, so new things coming, that means you actually have to redo it, right? So this is like really, really bad. It's like you have to, I mean, if you add one more user, I mean, if you add one more movie, you actually have to redo everything because your dimension of the matrix is different. So what we can do is, so this is basically called code stop problem. So and which is always a big issues. In fact, to overcome this, we actually have to leverage some side informations, not just the ID of the user and item. So what we can do is we can actually create some features for that. So basically, say these users and item has some features. And for example, this item, and for example, that movies actually has a name, has some director, or the name of actress. They all could be served as the features, right? So these movies is not just an ID, it actually has some features. So these features can be used in these kind of predictions. And all the information should be used in all sorts of rules, including these kind of and the movie features. And also with the user feature, for example, once you sign up those and a website, they will ask you whether you're female or male, and what is a birthday and an actress. So these could be your features as well for the users. So the goal is you want to predict some rating here. So one way that you can do is, instead of you trying to solve the A is approximate of W times A transpose, you want to wrap up this X and Y in the beginning and the end. So this is called inductive matrix completions. So this W and H is being like independent of the number of user or item. You can have like more users, you can have more items. This W and H will not be changed. So what actually is changing is just being the X and being the Y, right? So this is a very important things, because if we have a more data, more users that coming in, at least these two parts will not be changed, right? So everything else is being the same, right? So basically it's kind of like, and you can think about X as being the user features, Y is being item features. If you are giving a new user, you are giving a new items, they usually coming with the features. So that means if we can learn this W and H, if we have a more data, we can automatically get this A matrix. So without additional learning. So this is really good. But in any case, you can think about this XU, which is the feature of user U, and Y of I is the feature for user I. So you can think about previously my XU and and times W is actually the k-dimension embedding of the user U. H transpose of yi is actually k-dimension embedding for this movie I. So it's kind of, you multiply these two together becomes the embedding for the I. You multiply these two together becomes embedding for the user of U, and so on. Okay, so again, this inner product will give you some predictor value. So if we using this method, it becomes it's no longer being a cold start problem. That means we don't need to train my W and H again if we have a new data or new users, because usually the new data and new item on new users, these X and Y are like XU and YI are given. That are feature givens. So then this matrix A can just be automatically calculated out. So this is something called feature-based recommendations. Another way that we can do, which is a very, very popular one, I think, for the and project homeworks, you actually need to using this methods, because this will help you to come up with the new methods. So it's called factorization machine. So you can think about the following ways. In fact, we can transform our recommendation system into classification or regressions. But that is really good because classification and regression has a lot of methods, a lot of algorithm like XGBoost, random forest, and so on. Or even like using AutoML and AutoML and the frameworks, and which is really, really popular. So so here is basically, you can think about as the following. We have a U and I, right? So this is basically the user ID and I is the movie ID. But of course, like, and the U and I just is the integers. It's, and the worst situation what you can do is just simply just take the binary encodings, right? It's basically the binary encodings of the users and the binary and one-hot encodings for the movies, or dummy encodings for the movie. So basically, this is basically corresponding to the first movie. This is the first user, and so on, right? So, but if you have like more features can be extracted out, and then you are definitely feel free to do so. And so then you can think about this Z UI, it should be UI here, is the feature actually extracted for the user U and item I, right? So this is will be just corresponding to which user and corresponding to which movie. Of course, if we have more features from the users or more features from a movie, you can always keep putting into this Z here, right? Right. So right here, you can think about, so in this cases, right? So that would be XU and YI, right? So this will be, and that would be, the cases in this inductive matrix completion problem. Then you can also have like include all these kind of feature and information. For example, the other movie rated that you have, and also the time that you rate these movies, and the last movie rate, and so on. So basically, these can also be your features, right? So these are all the features. So basically, on each entry of the data, that you have the users a feature, you have a movie feature, you have other features that you have, for example, time and the other movie rated, right? So these are all like, and the features to make predictions of this ratings for that specific movies. Here, you just predict this to be 5. Basically, it says, I'm trying to, and the target is, that means for that first movie, the first user, and make the rating for that is 5, and so on. You can do this all the time. So Now this, and the beauty of everything right here is it actually turned a machine learning, a recommendation problems into a classification problems, right? And we have a features right here. And although this feature could be very, very large, and then we have a target. So the target is just 1, 2, 3, 4, 5, 1 to 5. Okay, so this is clearly to be an, and it could be think about as a regression problem as well, right? Because right here you can think about it's always has the way it is like 1, 2, 3, 4, 5, 5, and 5 is better than 4, 4 is better than 3, 3 better is 2, 2 better is it's better than 1. So you cannot just think about a 1 to 5 as being a classification problem, because in classification problem, you always think about a cat versus dogs. So you cannot think about cat is better than dog and so on. It's always like two independent categories. But in this movie rating things, you implicit has certain distances into the ratings, because 4 is better than 3, 3 is better than 2, and so on, right? So it's more like a regression problems that we have. But once you create this factorization machine, it automatically actually can be using all these kind of like regression algorithms that we already did, can be applied to this factorization problems. So this actually gives you a way. And once you have a new data coming in, for example, a new user, the same user, but like different movies, they haven't watched that, and these are all the features for the user of the movies. You can using this trained regressions problems to make a prediction for the target that hasn't been watched for that particularly combination of the user and the movies. Right. So this is kind of like very, very interesting ways that you actually can turn a recommendation systems into a regression problems. Okay, I'm not going to go through this into deep. So two details. There are multiple algorithms, and also like and multiple packages can help you to turn these problems into a regression problems. All right, so that's I want to talk about today. In fact, I think I'm running out of time. For this coding example, I'm doing that on the next lecture. This will be a very large data set. It's being very popular it's a test case of the recommendation systems. I will talk about this in great detail. And in fact, you are going to use similar data set in the homeowner projects. Okay, so all right, so that's all for today I want to talk about. Thank you.